landscape of modern air combat is a hyper-accelerated field of strategic conflict, a realm where tactical victory is no longer secured by the visual spectacle of a close-quarters dogfight, but by the silent, instantaneous exchange of digital information and terminal kinetic energy. Victory is often determined long before the aircraft visually acquire one another, resting entirely on the relentless aggregation of engineering minutiae, a complex algorithm where a single poorly manufactured component in a turbine blade or an outdated line of code in a threat library can serve as the fatal flaw that unravels an entire strategic plan. It is within this crucible of technological detail that military strategists must objectively assess the true combat parity between two of the world's most formidable 4.5 generation platforms, the Russian Sukhoi Su-35S Flanker-E and the Chinese Shenyang J-16 Qianlong. Both fighters trace their architectural DNA back to the legendary Soviet-era Sukhoi Su-27, but their evolutionary trajectories have diverged so radically that they now stand as archetypes of two distinct and often contradictory philosophies of aerial warfare. The Su-35S represents the kinetic zenith of the classic Soviet heavy interceptor design. Developed as the second deep modernization of the Su-27, the Su-35S was conceived in the early 2000s as a critical technological and operational bridge, an interim solution intended to provide high-end air superiority capability while the more complex and costly fifth-generation Sukhoi Su-57 program matured. Sukhoi designers focused on maximizing raw performance, streamlining the design by removing the canards present in earlier Su-27M derivatives, thereby shedding structural weight and complexity in a quest for unparalleled speed and agility. The resulting aircraft is defined by a singular purpose: aggressive air superiority, although it is cataloged as a multi-role fighter. Its tactical doctrine reflects a legacy mindset, expecting the fighter to operate as a high-performance spearhead, often supported heavily by dense, overlapping ground-based air defense networks. In sharp contrast, the Shenyang J-16 Qianlong, designated officially as a multi-role strike fighter, signifies a paradigm shift in Chinese doctrine, emphasizing sophisticated network integration over purely kinetic metrics. Derived initially from the licensed production Shenyang J-11, a local variant of the SU-27, and drawing heavily on the Russian SU-30 MKK multi-role architecture, the J-16's development signaled China's transition from mere reverse engineering to indigenous technological mastery. Crucially, the J-16 maintains a two-seat configuration, requiring a dedicated Weapon Systems Officer, WSO, in the aft cockpit, a configuration traditionally associated with strike platforms like the American F-15E Strike Eagle or the Russian Su-30 family. This is not a historical accident. It is a profound doctrinal statement. Managing complex electronic warfare, EW suites, coordinating real-time sensor fusion with remote assets such as the KJ-500 airborne early warning and control aircraft, commanding formation tactics, and simultaneously engaging multiple long-range air-to-air and ground strike targets imposes a cognitive burden that exceeds the capacity of a single aviator in a high-threat environment. The J-16 is explicitly built to function as a powerful, complex node within a vast distributed system of systems. The Su-35S, by limiting itself to a single seat, remains largely optimized for the intense, singular focus of the duel. The inherent divergence in design philosophy finds its most profound expression in the propulsion systems, where raw, high-performance aspiration collides with the gritty reality of industrial maturity and logistical sustainability. The Su-35S is defined by its reliance on two Saturn AL-41F1S turbofan engines. This engine, a derivative of the developmental engine intended for the SU-57 program, delivers immense thrust, cited at up to 33,000 pounds or 145 kilonewtons in afterburner, with maximum theoretical thrust potentially reaching 177 kilonewtons. This overwhelming power output is the foundation of the aircraft's celebrated extreme supermaneuverability. Furthermore, the AL-41F1S grants the Su-35S a limited ability to maintain supersonic speeds above Mach 1.1 without constant reliance on afterburner, a capability loosely termed supercruise. Crucially, the AL-41F1S integrates a sophisticated three-dimensional thrust vectoring control (TVC) system. This mechanical capability allows the exhaust nozzles to pivot, enabling breathtaking post-stall maneuvers like the Pugachev's Cobra and the Kolbit. While these demonstrations are undoubtedly spectacular for airshow crowds and provide undeniable advantages in the theoretical close-in dogfight scenario, the legendary merge, their practical utility in modern beyond visual range, BVR combat, is negligible. Contemporary air combat doctrine emphasizes retaining high kinetic energy, speed, and altitude to maximize missile range and agility. Executing a low-speed post-stall maneuver is tantamount to placing the aircraft deliberately inside the enemy missile's high-energy engagement basket, a tactical decision rendered suicidal by modern active radar homing weapons. This reliance on TVC, therefore, risks reducing the Su-35S from a formidable BVR threat to what some dryly observe as merely a spectacular dancing bear. In contrast, the J-16 relies on the indigenously manufactured Shenyang WS-10 series engines. Early variants, particularly the WS-10A, were characterized by persistent reliability issues, especially regarding compressor surge, and exhibited insufficient thrust. However, the program has achieved significant industrial maturity. The latest operational variants, such as the WS-10C, deliver an improved thrust of approximately 142 kilonewtons with reported thrust-to-weight ratios of 9.5 for the most advanced versions, bringing its performance capability into direct parity with established foreign non-thrust vectoring counterparts. China has also developed a TVC-enabled variant, the WS-10B3, demonstrating its ability to replicate the technology, but the J-16's standard deployment eschews this feature, prioritizing sustained kinetic performance and reliability over low-speed gymnastics. This comparison of engine technology leads directly to the most critical strategic differentiator: logistical resilience. Historically, high-performance Russian engines have been burdened by notoriously low mean time between overhaul, MTBO. While precise, contemporary data for the AL-41F1S is highly classified, related Sukhoi engines often require comprehensive overhaul after only a few hundred flight hours. The Chinese WS-10 program, starting from a low base, has reportedly achieved a technical life expectancy of up to 1,500 hours for its current models. This monumental difference in durability and service life imposes a staggering maintenance burden on the Su-35S fleet, drastically reducing its operational readiness, particularly during prolonged conflicts where logistical supply chains are strained or subject to international sanctions. The J-16, supported by a massive, mature, and entirely indigenous industrial base, commands a dramatically higher sustained combat availability, transforming the contest from a technical measure of peak thrust into a critical strategic assessment of availability versus availability. Both the Su-35S and the J-16 share the intrinsic radar cross-section, RCS, penalty associated with the original Sukhoi Su-27 architecture, characterized by large engine inlets, vertical stabilizers, and numerous non-contoured control surfaces. Neither aircraft is considered truly low observable, placing them firmly in the 4.5 generation, where they must rely heavily on electronic warfare and standoff tactics for survival. However, incremental differences in manufacturing and material science distinguish them. The J-16 has been the beneficiary of extensive technology transfer and design principles derived from the Chengdu J-20 fifth-generation stealth fighter program. This includes the integration of advanced radar-absorbing materials, RAM, and structural composites into the airframe. While these measures do not confer true stealth, they are designed to marginally mitigate the frontal RCS, particularly against high-frequency X-band threat radars. The goal is signal shaping and absorption sufficient to delay detection and compromise enemy fire control systems, providing a slight but crucial tactical breathing room in BVR scenarios. Conversely, while the SU-35S airframe represents the physical evolution of the flanker lineage, its production has, at times, reflected the broader constraints and quality control challenges endemic to the Russian aerospace industry. Though the SU-35S itself is generally considered structurally robust, analogous Russian programs, such as the initial production runs of the Su-57, have exhibited visible manufacturing inconsistencies, including misaligned panels, excessive gaps, and protruding fasteners. Such flaws, regardless of their origin, immediately compromise any attempt at low observable characteristics, increasing the inherent RCS. While direct systematic structural flaws on the operational Su-35S airframes are not widely documented, the contrast in industrial quality control and the material science inheritance derived from the J-20 program grant the J-16 a plausible, albeit marginal, advantage in subtle RCS reduction and overall structural finish and longevity. The long-term impact of the reliance on imported components and the pressures of wartime production on Su-35S airframe integrity remains a persistent strategic mystery. The most profound technological schism between these two heavyweight fighters is found in their respective sensor suites, specifically their primary fire control radars, the critical components that will determine which aircraft achieves first detection, first lock, and first shot opportunity. This is a fundamental battle between legacy power and digital sophistication. Passive electronically scanned array, PESA, versus active electronically scanned array, AESA. The Sukhoi Su-35S fields the powerful N035 Irbis-E PESA radar. The Irbis-E is renowned for its incredible raw peak power output and massive aperture, allowing it to reportedly detect large targets with a 3 square meter radar cross-section, RCS, up to 400 kilometers away in a narrow field of view. Its PESA architecture relies on a single, extremely powerful central transmitter source, feeding an array of phase shifters. The radar achieves a wide field of regard through a mechanical gimbal mount that physically steers the antenna, supplementing the electronic beam scanning. However, this power comes at a steep tactical price. PESA systems emit predictable, powerful main beams, making them equivalent to operating a high-powered searchlight in a dark battle space. The lack of low probability of intercept, LPI characteristics, means the Su-35S's transmissions are easily detected, tracked, and triangulated by enemy radar warning receivers, RWRs, at immense standoff distances. The fighter announces its position the moment it begins to search. Furthermore, while the Irbis-E boasts advanced ECCMA capabilities, its anti-jamming resilience and frequency agility are inherently limited by its reliance on a central power source and its complex architecture, making it highly susceptible to sophisticated digital radio frequency memory, DRFM, jamming techniques used by modern opponents. Against a typical fighter-sized target in a contested environment, the actual effective tracking range of the Irbis-E is estimated to be closer to 100 kilometers, a substantial discrepancy from brochure figures. The J-16 completely bypasses these liabilities by adopting an indigenous AESA radar, believed to be the type 1475 KLJX. AESA technology represents a quantum leap in sensor capability. Instead of a single transmitter, AESA uses thousands of small, solid-state, transmit-charge-receive (TR) modules. This distributed power allows for exceptional simultaneous multi-mode operation. The J-16 can perform air-to-air search, track-while scan against dozens of targets, conduct high-resolution synthetic aperture radar and SAR ground mapping, and passively listen for signals, all concurrently. Crucially, AESA technology is inherently superior in electronic resilience and low probability of intercept, LPI. By using rapid frequency hopping, variable waveforms, and low power per element, the J-16 can track targets surgically and covertly, vastly increasing its survivability in a dense electromagnetic environment. This AESA superiority, coupled with its large physical radar aperture, a benefit inherited from the original Flanker airframe, leads many analysts to regard the J-16's radar system as among the most powerful currently deployed by any operational fighter globally. In essence, the J-16 fights the information war with a digital scalpel, while the SU-35S must rely on a blunt, high-power instrument. The difference in sensor technology directly dictates the platform's respective roles in electronic warfare and networked operations. The SU-35S integrates the powerful L265M10 Kibini-M electronic countermeasures ECM suite. Kibini is a formidable defensive system, often housed in wingtip pods, designed primarily for self-protection. It employs digital radio frequency memory, DRFM techniques, frequency agility countermeasures, and false target generation to receive and distort incoming enemy radar signals. The goal of Kibini is not to destroy enemy assets, but to delay aircraft detection, mask the true target against false returns, cause range-finding difficulties, and degrade enemy track-while scan modes. Its use of gallium nitride, GaN, based ESA antennas for jamming transmission marks it as a modern and capable defensive shield. However, the Chinese approach emphasizes offensive electronic attack and dedicated network specialization. The standard J-16 airframe benefits from advanced data link integration with high-value assets such as the KJ-2000 and KJ-500 Airborne Early Warning and Control (AEW&C) platforms, enabling true real-time sensor fusion and seamless sharing of target tracks across formations. This ability to operate as a tightly connected network node amplifies the effectiveness of its AESA radar and weapons. Moreover, China has taken the decisive step of fielding the specialized Shenyang J-16D electronic warfare aircraft. This variant is a strategic asset dedicated to the suppression or destruction of enemy air defenses, CAD DEAD. Similar in concept to the American EA-18G Growler, the J-16D sacrifices its internal cannon and uses specialized high-powered jamming pods to conduct offensive electronic attacks. Its mission focus is to create intensely contested electromagnetic environments, effectively blinding entire radar grids, disrupting networked missile command links, and spoofing data links. The J-16D can carry specialized anti-radiation missiles, such as the YJ-91, to kinetically destroy targeted radars, clearing digital and physical corridors for subsequent kinetic strike packages or fifth-generation fighters like the J-20. This creation of a dedicated electronic attack platform within the J-16 family ensures that the Qianlong fleet functions as an indispensable force multiplier, an asymmetric capability that the single-seat, self-defending Su-35S fleet lacks. The J-16 is a distributed system. The Su-35S remains a centralized platform. The ultimate measure of any fighter lies in its lethality, which in modern combat is determined by its long-range missile suite. Here, the comparison becomes a fascinating duel between sheer velocity and terminal energy sustainment. The Su-35S boasts a significant threat capability derived from its ability to carry the enormous Wimpel R-37, NATO reporting name AA-13 Axe-Head missile. This specialized weapon, originally designed for the high-speed MiG-31 interceptor, is built for maximum reach with reported operational ranges cited between 150 and an astounding 400 kilometers. The R-37M is a hypersonic weapon capable of speeds up to Mach 6, making it ideal for targeting high-value airborne assets, HVA, such as AWACS, tankers, and bombers from extreme standoff distances. The Su-35S can carry up to 4 of these missiles, granting it an unparalleled initial reach that compels enemy HVA assets to operate at far greater and less efficient distances. For medium-range engagements, the Su-35S employs the R-77M, an upgraded version of the R-77 AA-12 Adder, which features conventional fins instead of the distinctive lattice control surfaces of its predecessor and is equipped with an active phased array antenna APAA seeker. This advanced seeker grants the missile a true fire-and-forget capability and a larger no-escape zone compared to older versions. The J-16 counters the Russian emphasis on initial range with a focus on sustained terminal lethality. Its primary beyond visual range BVR weapon is the PL-15 NATO CHAA-10 Abaddon. With a respectable operational range cited between 200 and 300 kilometers, the PL-15 matches or exceeds the R-77 and offers a unique technological advantage: the dual-pulse, solid-propellant rocket motor. In traditional missile engagements, the motor burns out early and the missile coasts toward the target, rapidly bleeding energy, making it susceptible to terminal evasive maneuvers. The PL-15's dual-pulse motor allows it to reignite its second pulse during the mid-course correction or terminal phase of flight. This injection of renewed propulsion ensures sustained hypersonic speeds, Mach 5+, during the endgame, dramatically increasing the size of the no-escape zone, NEZ, and ensuring a high kill probability, PK, even against rapidly maneuvering targets at maximum range. Like the R-77M, the PL-15 uses an advanced active radar homing seeker, but it also reportedly integrates a crucial home-on-jam HOJ feature. This allows the missile to track and destroy jamming emitters, turning the defensive electronic output of an enemy like the Su-35S into a terminal targeting vulnerability. Adding to its lethality profile, the J-16 is also reported to carry the very long-range PL-17, sometimes referenced as PL-20, an ultra-long-range missile designed explicitly to challenge the maximum reach limits of the R-37M. The multi-role capacity of the J-16 is further cemented by its heavy loadout capacity, 12 external hardpoints, supporting a comprehensive air-to-ground and maritime strike capability, including the YJ-12 heavy supersonic anti-ship missile, the YJ-91 anti-radiation missile, essential for SED, and various precision-guided munitions and standoff land attack cruise missiles, e.g. KD-88 and AKF-98. While the Su-35S is nominally multi-role, its operational utility and deployed weapon set remain heavily skewed toward air superiority. In evaluating these platforms, the contrast between on-paper specifications and in-the-field performance must be drawn. The Su-35S has undeniably gained invaluable, if sometimes negative, operational experience through its combat deployments, most significantly in the ongoing conflict in Ukraine. This intense use has provided painful, tangible evidence of the inherent limitations associated with advanced Russian platforms operating against layered, modernized air defenses. Logistical challenges, maintenance complexity compounded by the high wear rates of its high-performance engines, and the operational strain imposed by sanctions have demonstrably led to reduced operational readiness and heavy losses, validating the strategic risks associated with low MTBO figures and reliance on fractured supply chains. The J-16, meanwhile, benefits from an overwhelming scale of production and robust domestic industrial backing. Production rates have been immense, with estimates suggesting over 450 airframes in service by 2025. This massive production volume ensures standardization, simplifies logistics, and allows the platform to serve as the undisputed heavy backbone of the People's Liberation Army Air Force, PLAF, complementing the limited numbers of fifth-generation Chengdu J-20A fighters. The organizational structure of the PLAF has been undergoing significant, sustained modernization, including the transfer and consolidation of naval aviation and air defense assets under unified command structures, further streamlining the J-16's integration into joint warfare concepts. This continuous advancement, coupled with the ongoing technological bleed-down from the J-20 program into the J-16 airframe, positions the Qianlong not merely as a stopgap, but as a long-term, evolvable strategic asset designed to match or exceed the capabilities of comparable modern Western 4th and 4.5 generation fighters. The comparison thus transcends mere engine performance. It speaks to the underlying industrial health and strategic doctrine of the originating nations. The comparison between the Shenyang J-16 Qianlong and the Sukhoi Su-35S Flanker-E is not a simple choice between two variations of the same Soviet blueprint. It is an examination of two fundamentally different strategic priorities. The Su-35S is the pinnacle of the kinetic flanker concept, a high-speed, supermaneuverable fighter whose most compelling tactical advantage resides in its raw engine thrust and the staggering reach of the R-37M missile. It is a formidable single-seat interceptor optimized for the kinetic duel and for prosecuting high-value targets from extreme ranges, serving its function perfectly as an interim solution awaiting its fifth-generation successor. Conversely, the J-16 Qianlong is the expression of a mature, network-centric doctrine. It sacrifices the dramatic kinetic advantage of thrust vectoring for decisive, sustained informational and logistical superiority. Its advantages, the indigenous AESA radar, superior LPI and ECCM, the two-seat configuration, superior crew capacity for complex missions, the lethal dual-pulse PL-15 missile, superior terminal energy and HOJ capability, and the existence of the dedicated J-16D electronic attack variant, indispensable force multiplication, collectively grant it greater survivability, mission flexibility, and systemic lethality in a peer conflict scenario. Furthermore, the industrial maturity and high operational availability derived from the reliable WS-10 series engine and massive domestic production capacity ensure that the J-16 fleet, as a whole, possesses far greater strategic resilience against attrition and supply chain disruption. In the complex geometry of modern BVR combat, the platform that sees first, shares data fastest, tracks most covertly, and ensures superior terminal missile energy is the one destined to dominate the fight. Despite its architectural heritage, the Shenyang J-16 possesses the critical indigenous and digital advantages that position it as the superior strategic asset, a fully realized platform built for the integrated air warfare of the 21st century. The Su-35S remains a spectacular, powerful, but ultimately analog champion fighting a rapidly digitizing war. The preceding analysis centered on the critical technical elements that define airframe integrity, propulsion resilience, and the pure physics of lethal reach. Yet the calculus of air superiority extends far beyond the material limits of the airframe and the propulsive energy of its missile payload. The ultimate point of convergence for every sensor input, every tactical decision, and every fire control solution is the cockpit, the human-machine interface, HMI. It is here, in the final act of information processing, that the doctrinal differences between the single-seat Sukhoi Su-35s and the two-seat Shenyang J-16 Qianlong create a gulf that no amount of raw thrust can bridge. The Su-35S pilot operates within a cockpit environment that is a masterful fusion of analog legacy and digital modernization. It utilizes large, modern liquid crystal displays, LCDs, to present information, providing clarity for a pilot who must simultaneously serve as the fighter's radar operator, weapons system manager, electronic warfare coordinator, and formation commander. This workload, while achievable for an elite aviator, approaches the edge of human cognitive capacity during high-tempo combat, particularly in an environment saturated with digital threats and rapid tactical shifts. When the powerful SU-35 Airbus E-PISA radar initiates its high-power search, effectively illuminating the aircraft's presence to distant enemy passive receivers, the pilot must quickly integrate that data with input from the L265M10 Kibini M defensive jamming suite and the aircraft's crucial passive sensors, all while maintaining the high kinetic energy required for effective beyond visual range (BVR) missile employment. The SU-35S is designed to maximize the performance of one man, forcing that solitary operator to become a bottleneck for all incoming data. The J-16's philosophy explicitly rejects this single-operator cognitive choke point. Its tandem cockpit features two dedicated crew members, a pilot focused almost exclusively on the kinetic management of the airframe, and a weapon systems officer, WSO, in the rear seat, whose entire universe revolves around the network. This WSO is the indispensable maestro of the J-16's superior AESA radar, managing its complex multimode operations, searching, tracking, mapping, and passively listening, simultaneously and covertly. The WSO handles the administration of the intricate data links, coordinates with external assets like the KJ-500 airborne early warning and control aircraft, and manages the release of complex dual-pulse munitions like the PL-15. This division of labor not only drastically reduces the cognitive load on the pilot, enabling sharper kinetic maneuvers, but also allows the overall weapons system to function at a level of complexity impossible for a single operator. The J-16 functions as a distributed, two-person brain trust, capable of processing and acting on exponentially more tactical data than its single-seat counterpart. This architectural choice is perhaps the most eloquent statement on the divergence of doctrinal requirements. The Su-35S is designed for the high-altitude, high-speed duel, while the J-16 is built for the high-volume, information-intensive brawl. This reliance on an information network leads directly to the question of passive situational awareness, a critical silent aspect of modern air combat. Should a hostile environment compel both aircraft to switch off their active radar emissions to avoid detection, a moment of profound tactical silence, the comparison shifts to their electro-optical infrared EOIR sensor suites. The Su-35S is equipped with a formidable legacy in this domain, the Russian Optical Locating Station, OLS. This system allows the aircraft to passively detect the heat plume of enemy jet engines and the friction-induced heat signature of airframes moving at supersonic speeds, providing a critical ability to silently track and engage without emitting a single compromising radio signal. This capability, inherited from a long-standing Soviet doctrinal emphasis on passive detection, remains a major psychological and tactical threat, forcing opponents to fight an invisible duel. However, the J-16's passive sensors, though less openly documented, are integrated into a system designed for immediate, network-wide fusion. While the Su-35S pilot might detect an enemy silently with the OLS, that information must then be communicated, usually verbally or via a limited, secure data link, before a fire control solution can be generated. The J-16's WSO and its associated digital processing architecture ensure that all passive tracks, from its own IRST, from its wingman's radar, or from a distant KJ-500, are immediately correlated, fused, and displayed as a coherent threat picture on the multifunction displays. In the electronic quiet of a standoff engagement, this fused picture, seamlessly updated and distributed, transforms localized passive detection into a systemic advantage. Some advanced Chinese platforms, including variants of the J-16, are even exploring the integration of experimental systems that utilize artificial intelligence algorithms to manage these sensor fusion tasks autonomously, pushing the man-machine boundary further than purely contemporary Russian systems. The ultimate question is not which aircraft has a better optical sensor, but which can weaponize the resulting data most efficiently, and the J-16, backed by a dedicated WSO and sophisticated internal networking, has the inherent architectural lead. This relentless drive for technological sophistication within the Qianlong program is underpinned by an industrial apparatus that contrasts sharply with the challenges facing the Flanker-E. The J-16's lineage benefits from the sustained, high-volume manufacturing prowess of the Shenyang Aircraft Corporation and its dedicated supplier base. As the undisputed heavy backbone of the People's Liberation Army Air Force, PLAAF, production numbers have soared, with estimates suggesting over 450 airframes in service by 2025. This scale is not merely a matter of quantity. It imposes a continuous cycle of modernization, quality control, and logistical standardization across the fleet. Every new batch benefits from material improvements and software updates trickled down directly from the J-20 fifth-generation program, ensuring the J-16 remains current and relevant against the most advanced Western counterparts. The SU-35S, by contrast, operates under the perennial strain of a leaner, state-controlled system, heavily reliant on export orders to stabilize production and fund future development. The SU-35S has fulfilled its crucial function as an interim high-end platform for the Russian Aerospace Forces, VKS. However, its operational lifespan is now burdened by the inherent structural limitations of the high-wear AL-41F-1S engine, which, despite its dazzling performance, necessitates more frequent, costly overhauls compared to its Chinese-developed counterpart. The logistical challenges exposed during prolonged conflicts, from sanctions impeding component supply to the sheer difficulty of maintaining complex, high-performance engines in the field, undermine the platform's strategic readiness, effectively translating raw kinetic power into reduced fleet availability. The divergence in future trajectories is equally stark, resting on the relative maturity of their respective fifth-generation programs. The Su-35S was specifically designed as a technology bridge to the Sukhoi Su-27, intended to buy time until the newer, stealthier platform achieved critical mass. Yet the Su-57 program continues to face developmental hurdles and slower than anticipated production, forcing the Su-35S to bear the brunt of frontline operations and counter fifth-generation threats for far longer than initially intended. Its only real counter-stealth capability remains the speculative long-range detection offered by the Airbus E-PISA's ability to operate in L-band frequencies via secondary wing root arrays, a technical solution that still lacks conclusive, widely acknowledged effectiveness against high-end stealth platforms. The J-16, conversely, is evolving in lockstep with the Chengdu J-20. The Qianlong is designed to function as the indispensable force multiplier, the loyal wingman, and external missile truck for the limited numbers of the stealthier J-20. The J-16 can use its superior data fusion to identify targets and, crucially, to launch its long-range missiles, such as the PL-15 and the potentially hypersonic PL-17, toward the target, while the J-20 maintains stealth silence, acting merely as the forward target observer. In this dual-layered concept, the J-16's primary role is not to challenge the enemy's fifth-generation fighters kinetically, but to overwhelm the enemy's defensive system through sheer numbers, electronic attack via the J-16D variant, and the long-range volley fire coordinated by its WSO and AESA radar. Ultimately, the contest between the Shenyang J-16 Qianlong and the Sukhoi Su-35S Flanker-E is a proxy battle between two competing visions of 4.5-generation air power. The Su-35S is the final evolution of the analog heavy interceptor, maximizing single-platform performance through raw power and spectacular agility, embodying the legacy of the kinetic duel. The J-16, however, is the prototype of the networked multi-role strike fighter, leveraging industrial scale, indigenous AESA technology, and dual-crew operational capacity to achieve systemic informational superiority. In an era where air combat is less a sword fight and more a high-speed game of electronic chess, the platform designed to process and coordinate the largest, most accurate data picture is the one that holds the decisive, unseen advantage. The Flanker-E remains a brilliant soloist, but the Qianlong has become the conductor of a sophisticated, evolving orchestra.